All right. This video, I'm going to talk about stereographic projection. In particular, I'm going to talk about how we should be teaching in Calculus 2 because it's a systematic approach to a large family of integrals that you can do with just the methods of Cal 2, and they tend to get left out of the curriculum. And the ones that are done in Cal 2 tend to be done with rather ad hoc methods. So just as a simple example, kind of one of the first integrals that you learn after you learn logarithms, how to integrate secant. Well, somebody tells you, well, notice you can multiply secant x over 1, but multiply the numerator and denominator by secant plus tangent. Then this turns into secant squared plus secant tangent over secant plus tangent. And so if I integrate this, I get log secant plus tangent. But my question always has been, who just looks at secant and thinks, oh, I could multiply this by secant plus tangent over secant plus tangent? I mean, that first step seems to come out of the blue. And in fact, historically, this is not the way secant was originally integrated. It was originally integrated by Isaac Barrow using partial fractions. And it's not quite the same as what we're going to do, but it's very, very similar. So we'll talk about that here in a second. But before we jump into stereographic projection, let me just tell you the answer. So the substitution that winds up turning all trig into algebra is u equals tangent theta over 2. So, well, let me tell you the answer and then we'll go back and drive it. So if you do this, it winds up that cosine is 1 minus u squared over 1 plus u squared. Sine is 2u over 1 plus u squared. And d theta is 2 over 1 plus u squared du. So for example, if I wanted to integrate secant, secant of course is 1 over cosine. So integral 1 over cosine x dx. This would turn into integral of 1 plus u squared over 1 minus u squared. And then dx, so du is 2 over 1 plus u squared. Or sorry, d theta is 2 over 1 plus u squared du. So those cancel. And this turns into, if I do partial fractions, 1 minus u plus 1 plus u du. And if I integrate, this will have a negative on the log because of the minus. So this is log 1 plus u over 1 minus u. And if you want to turn it into the form you're familiar with, well, you just say, well, 1 plus u over 1 minus u. I can multiply top and bottom by 1 plus u. This turns into 1 plus u squared plus 2u over 1 minus u squared. These first two are secant. And then 2 over 1 minus u squared is tangent. So this is log secant plus tangent. But even if you don't do that last step to make it look like the familiar formula, the point is just getting the integral is incredibly simple. And it's also, I mean, it's just using partial fractions, which is something that hopefully we're teaching in our college algebra classes. I know a lot of them don't, but we should. So once we have this substitution, we can do this for any rational function that's got trig functions in it. We can turn it into an ordinary algebraic rational function and then solve it by partial fractions. But the complaint you might have is, well, where does that substitution come from? That doesn't seem any more intuitive than the secant plus tangent does it? Well, you can sort of answer that by saying, well, it doesn't, but at least this is universal. I mean, this will work not just for that integral of secant, but anything you wanted to do. But actually, this has a very simple geometric meaning, which is, as you probably guessed, this is stereographic projection. So let's see how that works. So we're going to draw the unit circle. So normal parameterization. So we have theta here. This is cosine theta and sine theta, right? We're going to do stereographic projection from this kind of west pole right here. So by geometry, this angle is half of theta. And then, so we see this is a line. It intersects at the x-axis at angle theta over 2. So tangent theta over 2 has a very simple geometric meaning, which is the slope of that line. So this strange substitution we were doing when we said u equals tangent theta over 2, u really is just, we're parameterizing the circle by the slope of the line if you make the circle starting at the west pole. Then there you go. Okay, so what would be the equation? Let's make sure we really do get the formulas we had before. What would be the equation for the line? Well, this is the point -1, 0. So we've got y minus 0 is slope times x minus -1, so x plus 1. We want to see where does that intersect the unit circle. X squared plus y squared is 1. So if I plug this in for y, I have x squared plus, actually let me flip that around, call it 1 plus x squared is 1. Doing that just because the next step, I'm going to subtract x squared from both sides. So I've got u squared times 1 plus x squared is 1 minus x squared, which is 1 minus x, 1 plus x. If x equals -1, that's this point right there. We don't care about that point. We care about this other point where it intersects. And so we can divide both sides by 1 plus x because it's not 0 except at that -1 point. So we've got u squared times 1 plus x is 1 minus x. U squared plus u squared x is 1 minus x if I guess the x's together. So I've got x plus u squared x is 1 minus u squared. Factor out the x and divide, so x is 1 minus u squared over 1 plus u squared. And of course, the usual parameterization is x is equal to cosine theta. So sure enough, cosine theta is 1 minus u squared over 1 plus u squared in this stereographic projection. Let's go ahead and do the other one too. So this is theta, this is cosine theta, sine theta. So I've got y equals u times 1 plus x. In other words, y over u. I can't draw a u when I've got a y that close. Minus 1 would be my x. So if I plug that into x squared plus y squared is 1. So I've got y over u minus 1 squared plus y squared is 1. So y squared over u squared, 2y over u plus 1 plus y squared is 1. The 1's cancel. And again, at the point I care about, y is not equal to 0, or I mean, y is only equal to 0 there, and this is kind of a limiting case where it's not. So anyway, I can divide everything by y. So I've got y over u squared minus 2 over u plus y equals 0. If I move that guy to the other side, I've got y 1 over u squared plus 1 is 2 over u. And so y would be 2 over u over 1 over u squared plus 1. Multiply the top and bottom by u squared. This is 2u over 1 plus u squared. So sure enough, in the stereographic projection, sine theta is 2u over 1 plus u squared. And then so that's where the first two formulas come from. Of course, you can also verify them directly just from if u equals tangent theta over 2. Don't do any geometry, like for example, well, let's just do the sine one. Sine theta would be 2 sine theta over 2 cosine theta over 2, right? Which is 2 tangent theta over 2 times cosine squared, since tangent is sine over cosine. Well, tangent theta over 2 is u. Cosine squared, well, I know 1 plus tangent squared is secant squared, right? So cosine squared would be 1 over 1 plus u squared. So you can verify them directly just using trig identity. It's pretty simple, but that would kind of miss the point. I mean, the point is that this is actually a very simple geometric picture that motivates this trig substitution. And then let's go ahead and check the last one. So what about d theta? So if u is tangent theta over 2, then du would be secant squared theta over 2. And as we just said, secant squared is 1 plus tangent squared. So du is a half 1 plus u squared d theta. So d theta is 2 u squared du. Okay, so we've checked to see if this thing really works. And the great thing about this is that it turns any rational function that has trig functions in it into a regular one. So sure enough, we did secant at the beginning, but let's go a little later on in calculus 2. If I want to integrate something like that, well, in calculus 2, you learn to turn this into secant cubed by saying x equals tangent theta, right? And then this one, you practice your integration by parts. Well, it's certainly worthwhile to practice integration by parts, but you could also do this with partial fractions now, because secant is 1 over cosine. So this would be 1 plus u squared over 1 minus u squared cubed. And then d theta is 2 for 1 plus u squared. Oops. So, I mean, it's a little ugly because, well, first of all, those do cancel. So I've got 1 plus u squared over 1 minus u squared cubed. But the point is this denominator splits. So we'll get a term that looks like a over 1 minus u, b over 1 minus u squared, c over 1 minus u cubed, d over 1 plus u, e over 1 plus u squared, f over 1 plus u cubed. So I mean, actually getting that partial fraction expression takes a good deal of algebra, but honestly, I don't know that it's a whole lot harder than doing the reduction formula for secant. So, I mean, you put in your work one way or the other, but these are all very easy to integrate once you've got to this point. So the integration part is trivial. It's just doing the algebra to write this out into partial fractions. And it's not just limited to this. We can do a lot of integrals that we normally don't do in a calculus 2 class using the substitution. Like say if I want to integrate something like, let's do 8 sine x minus 4 cosine cubed of x over cosine of 2x plus 5 sine of, I don't remember what my sine of like 3x or something is off the top of my head. Sure, I'll go ahead and put it down even though I don't remember it. So in principle, this is no big deal either, right? You've got 8, sine turns into 2u over 1 plus u squared. 4 cosine is 1 minus u squared, 1 plus u squared cubed. Cosine 2x is 2 cosine squared x minus 1. So it'd have 2, 1 minus u squared over 1 plus u squared squared minus 1. And then 5, I don't remember what sine is, but sine 3x is some number times sine cubed of x plus some number times sine x. So anyway, up to figuring out what these two numbers are, which is just a simple trig problem. This is 2u over 1 plus u squared, and then some other number, or sorry, cubed, 2u over 1 plus u squared. And then, of course, you've got the du term, so the 2 du over 1 plus u squared. Again, this is a lot of algebra that's going to go into this, but plus algebra plus partial fractions. And all of a sudden you get an easy integral. So, I mean, here's all your work is doing algebra and do partial fractions. Once you do all that, the actual integration is simple. And this, I'm sure you would agree, is probably not a problem you've given your calculus 2 students anytime in the recent past. But in principle, it's not any harder than integrating secant or integrating secant cubed. So, moral of the story is, I think we should really teach this substitution in Cal 2 because for two reasons. One is pragmatic in that it turns any rational function composed with trig function into just an algebraic rational function. And so that's the pragmatic reason. But the other reason is it's also easy to motivate in that this geometrically, this is just stereographic projection, which is a very important parameterization of the circle that they're going to need to understand it once they get to differential geometry anyway. It certainly doesn't hurt to go ahead and show them that you can parameterize the circle this way, even back in their calculus class. And they can see the benefit of parameterizing the circle this way in that they turn all these circular functions, aka trig functions, into regular rational algebraic functions. So anyway, I think we need to start teaching that in Cal 2.